this should be welcome back. Hopefully you've seen part one of this inverse functions. Just as a reminder, probably the most primary fundamental thing to keep in mind on inverse functions is compared to the original function, they turn the x's into the y's and the y's into the x's. So exercise 59 through 70, determine algebraically whether the function is one-to-one. So we learned that looking at the graph, we can use the horizontal line test to determine if a function is one-to-one on the last video. For the algebraic test, we're just going to go through the process of trying to find the inverse. And if all goes well and we only end up with one solution as we solve for the inverse function, then it is one-to-one. In this case, I would have 3y equals x subtract 5 away, and I end up with y equals x minus 5 on 3. That is the inverse function, f inverse of x. So if I take a look at this. If I put 4 in here, I get 12 plus 5, 17. If I put 17 in here, I get 17 minus 5, 12 divided by 3. I get back to 4. So this contains 4, 17, and this graph contains 17, 4. So determine algebraically whether the function is one-to-one. Verify your answer graphically. If the function is one-to-one, find its inverse. We did. Okay, so you might say, well, we can always find an inverse function then. Let's take a look. Here's 64. So 64, my new x equals 4x squared, or excuse me, 4 on y squared. I'm going to cross multiply. Xy squared equals 4. I'm solving for y, so y squared equals 4 on x, or y equals plus or minus 2 on square root of x. When I take the square root of both sides, I have to use a plus or minus, which means when I put, say, 16 in here, I get 2 on 4, I get 1/2, but I get plus or minus 1/2. That's a dead giveaway. This is not one-to-one. If in the process of solving for y, we introduce a plus or minus, it is not one-to-one. Determine whether the function is one-to-one. It is not one-to-one. Okay, 68, which I gave almost no room for some reason here on this sheet. I'm going to steal some room from up here. So x becomes y becomes x. So that f of xy becomes an x equals square root of x minus 2, y minus 2, come on. I square both sides, I get x squared equals y minus 2, and y equals x squared plus 2. Now we got a little bit of a challenge here, because if I take a look at the graph of this first function, this is a square root function. It wants to look like that, except it's down 2. This is a sideways parabola. If I solve this for x squared, it's x squared minus 2. The graph of this thing wants to look like, well, this is x squared plus 2. This is this is an up and down parabola. I was saying this is half of a sideways parabola. This parabola, as we know, wants to look like this. So it's not the entire parabola. The part that is symmetric across y equals x is just this portion of it, or the portion where x is greater than or equal to 0, and we have to state that. So got to be careful with that. If you end up with a function that's not one-to-one, then we're going to have to restrict domain. And that's discussed here. Restrict the domain of the function so that the function is one-to-one. We know that the graph of this, hopefully we know this, looks like that. There's the graph of our function. We want it to be one-to-one. So I can either lop it off to the left or lop it off to the right. I'm going to lop it off to the right, and we'll talk about what happens if we lop it off to the left. So we're going to say, okay, this is one-to-one when x is greater than or equal to 2. So all we're really looking at is this portion of that absolute value curve. Okay, so replace the y with x, replace the x with y. how do we get rid of absolute values? Well, if I had absolute value of x equaled 3, then we would say x equals plus or minus 3. So I'm going to go x, or y minus 2, I guess. Y minus 2 equals plus or minus x. So y equals plus or minus x plus 2. Let's take a look. Well, that's y equals x plus 2. Y equals x minus 2. Or, wrong. Y equals negative x plus 2. Let's consider that for a moment. If I draw this one in red, y equals x plus 2 would be this line. Y equals negative x plus 2 would be this line. Which of those lines is the inverse of that line? Well, this part of it is, because we know that it's reflective over the line y equals x, and that's where this would reflect to. But it's not the entire line. It starts right there. So we would say our inverse function is the x plus 2. Inverse function of x is x plus 2, but only when x is greater than or equal to 0. See, this point 2, 0 becomes 0, 2. All right, a little bit sneaky there. I think the graph's almost critical for this to get an idea what the graph looks like. So on 88, let's take a look at what the graph of this looks like. This has a right side. This is a quadratic, of course. It's a parabola. It's up 1, and it's not growing quite as fast, but it definitely is going up. It wants to look like this, and it wants to look like that red one. The blue inverse would have to look something like, I guess, this, and maybe they cross or touch because it's symmetric across y equals x. And the red, if I can imagine flipping that over here, would look something like that. This guy flips over to there. So we don't really get a rotated parabola, we actually get a flipped over parabola. So it just depends on what side we want to talk about. For instance, let's say I want to just lop this one off that way, and I would probably recommend going with the opposite, but I'm going to go x is less than or equal to 0. Let's see what happens here. So y's become x's, x's become y's. We solve for x, and I get x minus 1 is 1/2 y squared, or y squared is 2x minus 2, or y is square root plus or minus square root of 2x minus 2. I think I'm going to make that, I think I'll leave it like that. I think I'll leave it just like that. Okay, so we take a look at this guy, and this would be a top, the plus would be the top half. It's that portion, and that came from where this graph was greater than or equal to 0, but we said less than or equal to 0. So I would actually want to go with the answer y equals the bottom half, 2x, try again, y equals square root of 2x minus 2. We want the bottom half of that curve. But again, typically I would probably go with the top if we talk about the blue inverse. So this would be the red inverse of x. The blue inverse of x, f inverse x, would be, the red one's the negative. The blue one is the positive, 2x minus 2. It's the top half. Okay, and 91 through 92, in exercise 91 and 92, use the graph of the function f to complete the table and sketch the graph of f inverse. Well, once again, if we remember this very simple idea, x's become y's, y's become x's, and we say on f there is a point 3, 3. This is 3, 3. And on x there is a point 1, 2, and on x we've got a point 0, 0. I'm not going to list it, it's pretty clear. This point is at -1, -2, and here's a point at -2, -4. If those are defining points excuse me, of f, if -2, -4 is on f, what must be on f inverse? -4, -2. If 1, 2 is on f, what must be on f inverse? 2, 1. If -1, -2 is on f, then -2, -1 must be on f inverse. And if 3, 3 is on f, switch them, 3, 3 must be on f inverse. So a quick sketch, -1, 2, 3, 4. I've got to go as high as 3. I've got to go to the right as far as 3, and I've got to go down as far as 2. -4 gets me -2. -2 gets me -1. 2 gets me up to 1. And 3 gets me up to 3. We've got, and 0 gets me at 0. That was 2 gets me, that was bad. 2 gets me up to 1. So we've got this graph. Once again, note, increasing, and I think you can kind of see if we would reflect that over y equals x, we'd be in pretty good shape here. Okay, here's some fun ones. In exercise 93, use the graphs of y equals f of x and y equals g of x to evaluate the function. I want g inverse of 0. Well, g inverse, g is a factory that takes zeros and turns those into 2. So does that have anything to do with what we're talking about? This is what g does. G turns zeros into 2, so g inverse turns 2's into zeros. That's not helpful here. I want to know what g inverse turns zeros into. See, normally we put x's in here, but because it's an inverse function, on the plane function, this is the y value. So we kind of look at this sideways and we say, oh, 0 becomes -2. That's the point -2, 0 on g. So 0 becomes -2. Okay. So 96. First, we're going to start inside. F of -4, that's plain old f of -4. F of -4 is 4. So I need g of 4. Plain old g of 4 is 6. No inverse functions there. Here we've got g inverse of f of 3. And plain old f of 3, f of 3 appears to be 5. So that's g inverse of 5. That's g inverse. Oh, I looked at the wrong one. I was looking at g. I need g inverse. F of 3, 1, 2, 3 on f. F of 3 appears to be -2. Okay, now I look at g inverse of -2. That means I look, this is a y value of g. So the y value of g associates over here to what appears to be -3. Highly recommend give 100 a quick try. Might want to pause, take a minute or two, try to figure out 100. Okay, once again, hopefully this is welcome back. This is f inverse of g inverse of 6. So I'm putting 6 into g inverse. This is g. G inverse, I want to look at 6 as the y value. The y value we put in 6 turns it into 4. See, g has the point 4, 6 on it. So g inverse would have the point 6, 4. So this is f inverse of 4. So that's saying, when does f's y value become 4? F's y value becomes 4 over here at -4. So just a whole different way of looking things, but once again, the big key, x's become y's, y's become x's. If there was a struggle on this, then my recommendation would be just to create F's t-chart, create G's t-chart, and then from there, if you've got F's t-chart, which would be, for instance, I'm not going to do it all, we've got -4, 4, 0, 2, etc. Then we could do an F inverse. That would be 4, -4, 2, 0, ... And from there, I believe you'd be in good shape. Okay, here is your assignment that's all over the place. And I probably should have had that on the first video because this is going to be a couple days we're going to be working on this. I'm certain there's going to be questions. But pretty important concepts for us. Inverse functions. It becomes a really big deal when you get into calculus. Okay. Let me know if I can be of any help, and best wishes.